Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll assess the performance of a single GPU on either the Accel or the A100 nodes by measuring its efficiency in matrix multiplication, expressed in gigaflops per second. We've previously outlined the GPU testing Python script that we'll utilize for this evaluation. We'll use a matrix dimension of 16384 for matrix multiplication in our Fortran program with the file ending 1. In the Python testing GPU script, we set the GPU offloading method to use the do concurrent approach, as explained in our previous video. The initial test will involve applying the Fortran program with the file ending 1. We need to remember to update the value of n in our Python testing GPU script, and we'll set the billing factor to 6. Before we begin GPU testing, we need to update our setup script. We'll use n equal to 16,384 and request 7 GB on the Accel node. We need to remember to use our new alias, nvhpc, to load the latest NV Fortran compiler. After executing the setup script, we verify using our alias CPU bill that the billing factor is 6, as assumed in our testing script. Now, we've transitioned to the C7-8 node and are ready to conduct our initial test with a single Nvidia P100 GPU. We use the testing GPU Python script, which displays the compilation command and then proceeds to execute it. Following the compilation, various warnings and notes are shown on the terminal. Let's filter out these warnings and notes. The wall time is approximately 65 seconds, while the CPU time is 6 times longer than the wall time. Based on the wall time, the performance is around 136 gigaflops per second, and based on the CPU time, it's about 23 gigaflops per second. We can examine the monitor file produced by the testing GPU script, and we observe that the GPU performance is recorded every second. We notice that both the GPU and memory utilization reach 100% after about 4 seconds. As we continue scrolling through the monitor file, we can see the transition from the end of the first test, which lasted about 65 seconds, to the start of the second test. In the next test, we'll use the Fortran program with file ending 2, ensuring that the value of n is set to 16,384. Let's apply the loop interchange technique performed by the Intel Fortran compiler. Now, the J loop is the outer loop, and the I loop is the inner loop. We'll save this version with the file ending equal to 2. We need to update our Python testing GPU script and specify that we'll use the Fortran program with file ending 2. We conduct one more test with the interchanged loops, and as previously, we encounter some warnings and notes. Let's remove them again. Now, the wall time has reduced to around 36 seconds. This suggests that the NV Fortran compiler couldn't execute the loop interchange as efficiently as the Intel compiler did. Consequently, the measured performance has risen to about 241 gigaflops per second based on wall time and around 40 gigaflops per second based on CPU time. Notably, this last measurement of 40 aligns closely with the result obtained using one CPU core in our Fortran optimization video. Upon inspecting the monitor file, we observe that the memory utilization has decreased to approximately 51%, while the GPU utilization remains at 100%. As we scroll down, we reach the point where the first test concludes after approximately 36 seconds, and the second test begins. What performance can we expect from the A100 Nvidia GPU? These nodes operate on a different architecture. Unlike the P100 GPUs on the Accel nodes, which were hosted by Intel CPUs, the A100 GPUs are hosted by AMD CPUs. Therefore, after transitioning to an A100 node, we need to switch the standard environment from one that supports Intel to one that supports AMD. This is achieved by utilizing the module swap command with the force option. Once more, we execute our setup script to request migration to one of the A100 nodes. We confirm the CPU billing using our alias CPU bill and update our testing script with CPU billing set to 8. As noted, we need to switch our environment to one compatible with the AMD architecture. In our Python testing GPU script, we specify that we'll now conduct testing on the A100 GPUs, and we'll continue to use the Fortran program with file ending 2. We need to ensure that the value of n is accurate, and we're setting the billing factor to 8. We'll use the program with file ending 2, employing the interchanged loops, as the NV Fortran compiler isn't capable of performing this optimization. Employing our testing GPU script will generate some warnings and notes, which we can mask out just like before. The testing script displays the compilation command and then executes it. Notice that the script has updated the GPU specification to CC80 and removed the march option for the Skylake architecture, as it's specific to Intel architecture. Notably, the wall time has decreased to approximately 8 seconds, while the CPU time is 8 times longer due to the billing factor. Performance has surged to about 1,067 gigaflops per second based on wall time, and approximately 133 gigaflops per second based on CPU time. In the monitor file, we continue to observe GPU and memory utilization as before. Notably, the wall time for a single test is short, lasting only about 8 seconds. Now, let's reconsider the performance on the A100 node by scaling up the matrix size, setting n equal to 32,768. Setting n equal to 32,768 will quadruple the memory requirement compared to when n is equal to 16,384. Thus, in our setup script, we'll request 26 gigabytes of memory to meet this increased demand. In the Fortran program with the file extension 2, we need to update the value of n to 32,768. In our Python testing GPU script, we need to update the value of n to 32,768, and we'll set the billing factor to 8. Executing the setup script transfers us to the GPU 12.7 node, where we use our alias CPU bill to confirm that the billing factor remains at 8. Once again, we must transition our environment to one that supports the AMD architecture. Using the testing GPU script on the GPU 12.7 node yields warnings and notes, which we can eliminate for clarity, as done previously. Doubling the size of n results in an 8-fold increase in flops. Despite this, the wall time only extends to about 57 seconds from the previous 8 seconds in our last test. Enlarging the matrix size enhances the GPU performance. Now, the measurement stands at about 1,230 gigaflops per second based on wall time and approximately 154 gigaflops per second based on CPU time. This performance level is higher than what we achieved with the P100 GPU, which is natural given that the A100 have 6,912 cores compared to the 3,584 cores of the P100. Let's summarize the advancements covered in our recent videos. Initially, in the Fortran compiling video, the matrix multiplication performance with the TMP variable was below 1 gigaflops. However, by adjusting the accumulative summation method, we increased the performance to around 6 gigaflops per second. After specifying the architecture with a 512 bits AVX vector register, performance surged to about 12 gigaflops. Subsequently, in our Fortran optimization video, enabling interprocedural optimizations with the IPO option pushed performance to roughly 17 gigaflops per second. Utilizing the highly optimized mat-mul routine from the Intel Fortran compiler propelled performance to about 45 gigaflops per second. Now, leveraging parallel computing on one GPU has resulted in performance levels of about 40 and 154 gigaflops per second based on CPU time. As we'll discuss in our upcoming video, this CPU time metric provides the best comparison for GPU performance against multi-core computing or parallel computing using many CPU cores. In our upcoming video, we'll explore GPU offloading using OpenACC directives. OpenACC, or Open Accelerators, is a set of directives for parallel computing. It's designed to simplify the process of accelerating applications on heterogeneous computing systems, such as GPUs and other accelerators. OpenACC allows programmers to specify regions of code that should be offloaded to accelerators, enabling them to take advantage of the computational power of these devices without having to rewrite the entire codebase. I am looking forward to the next video. Wishing you all happy computing in the meantime.